Oh, hey everyone. Thanks again for joining us today. My name is Young, and I'm a research scientist at Abacus. I'm very thrilled to chat with our panelist, Dilip, about AI and robotics today. Nice to meet you, Dilip.
Nice to meet you, Yang.
Please allow me to give a brief introduction of Dilip. So Dilip is a neuroscientist and co-founder of Vicarious, and he got his PhD from Stanford and was visiting fellow at the Redwood Center for Theoretical Neuroscience at UC Berkeley. And some of his work include hierarchical temporal memory and AI models that break text-based CAPTCHAs. And I guess without further ado, let's get started. So I'd like to kick things off with some big picture questions. So nowadays, when people actually talk about robotics, this concept is often like bundled with AI and deep learning. But what was the field like before the advent of deep learning, and what did deep learning bring to the field?
Thanks, Yang, and thanks for the introduction. I want to make one correction. I'm not officially a neuroscientist. My background is like an undergrad, PhD, all are in electrical engineering with machine learning, and then I started studying neuroscience because it is relevant for machine learning. So, theoretically, I'm degree-wise
You're
not a
like
neuroscientist.
interdisciplinary scientist.
So I published in neuroscience. Okay, now coming to the question. So if you look at traditionally where robotics has been applied, it's in industries where the manufacturing process is extremely stable for 5-10 years. One example is car manufacturing, where once the car is designed, you need to make hundreds of thousands of copies of it, and that design is really stable for 5 years, and each product, each copy is $30,000. So you can afford to make a manufacturing facility, program the robots, take a year and a half to program those robots, but the cost of programming those robots can be amortized over the lifetime of the product. And the programming there is all about going from fixed location to fixed location. So if you look at what the robots are doing in these manufacturing facilities, they don't even have cameras on them. So it's a 6 or 7 degree of freedom arm. It is programmed to go to position 1, do something like turn on the gripper, do suction or something like that, move to position 2, do another operation, turn off the gripper, release the item, or pick up another item. So it's hard-coded position-to-position programming, and that's what robotics has been for quite a large number of years, and it has been very successful in the automotive industry. But many of the problems that we deal with, many of the products that we consume are not like this. The products change every year or every month, and you need to deal with very variable situations, whether it is handling packages in a warehouse or kitting items into a box, making secondary packaging for retail outlets. All of these things require handling variability. So you have to deal with variable objects, variable placement. Nothing is coming on a fixture. So for that, you need to perceive the world. You need to look through a camera and understand what is happening, so that you can pick objects from cluttered bins. You can manipulate them. You can assemble them. All of these things. So now the hardware, the robot is not driven by position coordinates, but by camera driven. Okay, here is what to grasp, here is where to insert, etc. And here is where deep learning has made a difference. We all know that deep learning is good at many perception tasks, and I would put it this way: deep learning has shown us the promised land, but deep learning alone won't be able to take us there. And the challenges there are, we are all familiar with those challenges. It takes a lot of data to train deep learning to do a particular task, and if the task description changes or some other condition changes, if the distribution of the data changes, what we call the distribution shift, then deep learning fails or generalizes poorly. And this is a challenge in robotics, because you can simulate a lot of data in your lab and train a system, but in the warehouse, if there is a new light introduced, or if there is sunlight falling from one side, then suddenly you are off and you have to simulate that situation and data augment. And so although deep learning has opened the doors for us, deep learning alone won't be enough with rapidly changing situations. And that is why we early on invested in developing alternative techniques. And deep learning has started moving in these directions, which is to have more structured models, models that have more inductive biases, make more assumptions, models that can deal with uncertainty better than deep learning currently. So deep learning is, when you abstract away, it is a function fitting paradigm. It is, here is a set of inputs, here is a set of outputs you want to map from the inputs to the outputs. It's a function approximation paradigm. And what is missing in that deep learning paradigm is mechanisms for efficiently dealing with uncertainty, mechanisms to do dynamic inference. By this, I mean, since it's a function approximation paradigm, what you call inference in graphical models is converted to amortized inference in deep learning, where you are training for a particular query. Whereas what you can do if you have a good model of the world is you can train a model of the world and change the query dynamically and do inference dynamically. All those things become important when the world is dynamic. So developing new versions of deep learning, whether you call it deep learning or a merge of graphical models, probabilistic techniques and deep learning, it doesn't matter, but that's a direction everybody has to go in, and having more structured models. And that's what we invested in pretty early on. And that is definitely giving us a big advantage in deployments, because there are places where it is extremely expensive to data augment to solve a particular perception problem, whereas the techniques that we developed, which is called recursive cortical network, works very well without those data augmentation, and it is giving us a good advantage in robotics in deployments.
Thank you. That's a very interesting answer. Yeah, I think especially for a younger generation, like when we think about, like, I don't know if I belong to the younger generation, but when people in the younger generation think about, robotics, there's this sci-fi thing that they mentally picture, right? And you don't often think about, all those robotic arms have already been serving like car factories, as you mentioned, and other factories for decades, right?
Exactly. Yeah.
And also, like, I really appreciate your insight on data efficiency, also like dealing with the dynamically changing environments. I think those are really good insights. All right. So moving on to the next question. I know that you mentioned that your work is on, say, brain-inspired AI research. And what are some examples of AI developments, borrowing ideas that's borrowed ideas from brain science that actually inspired you, your own research at this intersection of AI and neuroscience?
Yeah. So even when you go back to early days of deep learning, I attended one of the first summer schools in deep learning, which was some 20 odd students in Toronto, and Jeff Hinton was giving the tutorials, and then many of the people that now we are familiar with were there, and Jeff Hinton was paying, because some glitch with the stipend. Jeff Hinton was paying out cash to every attendee from his pocket, saying, "Oh, we will figure out the stipend later." And so even in those early days, there were people. Even Jeff Hinton himself is motivated by the brain and looking at brain to find principles to apply to build machines. In fact, one of his papers before deep learning became the big thing was called "What Kind of Graphical Model is the Brain?" He didn't ask what kind of neural network is the brain, because the title was "What Kind of Graphical Model is the Brain?" So people, at least the pioneers in this field, have had this notion of deriving insights from neuroscience, and because that's because what's our ultimate goal? Our ultimate goal is to build machines that are as versatile and smart as humans. And humans are the only proof of concept that we have for something like this is possible. And so it makes sense to look to neuroscience to get inspiration. And in fact, convolutional neural networks and the precursor to convolutional neural networks, which is neocognitron, is an example of an architecture that is derived from neuroscience. The idea of local receptive fields, then pooling the local receptive fields to build higher level invariants, and then building another level of features. This idea came from neuroscience. This is called the Hubel and Wiesel model of visual processing, and this is what neocognitron was based on, and then it got adapted into the neural network architectures using convolution as the operation and weight sharing. So I would basically put one of our works, the paper that we published in Science, as an example of how to use insights from neuroscience to improve the models. And so the way to look at it is this. Your brain is making assumptions about the world. The only reason why your brain is good at things like vision, language, etc., are because your brain is making assumptions about the world, because there is no free lunch. There is no algorithm that can do everything equally well. So by looking at the brain, you can figure out what those assumptions are, and you can also get insights on how those assumptions are encoded. You don't want it to be very, very, you don't want it to be hacks. You want it to be general principles, and you can then learn those general principles and put those into your models in a way that makes sense. And one example I can use from our work is this idea called shape and appearance factorization. When you as humans, when we look at objects, we treat the texture of the object separately from the shape of the object, the form of the object. So if I show you a chair made of ice, you won't get confused. You'll say, oh, it's a chair made of ice. And if I change the material on it, you won't get confused, because the shape is represented separately from the color or the texture of the object. This is an insight that has been in neuroscience for a long time. You can see that in the structure of how the visual cortex is built and in the connection that this factorization exists. It's not an idea that is used in deep learning currently. There are maybe one or two models trying to do it, but this is an example of a piece of insight that we used in our model. And then if you look into neuroscience, you also get examples of how to actually do it. It's not just, oh, this property exists. It's also how can you encode it in neural networks or graphical models. And this is a general principle. Shape and appearance factorization is not a principle that is just for visual processing. So this is about structure of signals in the world. If you look at natural signals, basically you have two levels of continuity in the natural signals. What you can observe is that any discontinuity of an n-dimensional signal is also smooth in the n-1 dimension. So it's for example, when you look at images, the discontinuities are the line segments, the lines that partition the image into different regions, and the lines themselves are continuous. They are continuous in 1D. So piecewise continuity at two levels, and this property corresponds to something like shape and appearance factorization in visual system. But the same principle can be also applied to fluid dynamics, shock waves. All of them have this property. So this is an example of looking at the brain to see a property, then finding out what is the underlying principle behind that, and then applying it to a wide variety of architectures. And another example is the use of feedback. Neural networks are mostly feed-forward engines. Brain, there are more feedback connections than feed-forward connections. What are they doing? And that's another example we used in our paper, that these feedback connections are important for dynamic inference, not just amortized inference. And you can see that when you are looking at Hinton's new papers, he is also basically starting to say the same things. It cannot be just a feed-forward engine. Feedback is important. So some examples, hopefully those help.
Yeah, I think there's some great insights and examples. Yeah, I've been reading some papers recently on how like very deep feed-forward neural networks are actually kind of trying to approximate the feedback
Yeah,
connections in our real brain.
yeah.
Yeah, that's some very insightful ideas. And can you tell us more? I think you were mentioning like your work about like the feedback. Was the example about how you build the model that break the captcha challenge? Or
Mhm.
that's nice.
Yeah,
And
yeah, yeah. It had feedback in it because and it is very easy to understand the role of feedback and how it is mimicked in deep neural networks. So basically, what happens is when you are parsing a captcha, captchas are confusing for humans because you bring the characters together and clutter them, right? You make them and what happens is that now you start seeing new characters in the juxtaposition of the other characters. You can look at, oh, these two characters together start looking like a character to you, and you can get confused. And why do humans not get confused? Because they can look at the whole captcha and explain away, oh, this thing that looked like a character in between is not really a character because it doesn't make sense in the whole picture. This is called explaining away. You are looking at a local picture and saying that doesn't make sense because it doesn't make sense in the global thing, although the local evidence is very strong for there being a character, a hallucinated character there. So this explaining away is a dynamic process in humans. This is happening at runtime. It is not happening at training time. So you can just train on single characters and still have the property of explaining away. So that's why humans are very good at cracking captchas without explicitly training on captchas. Deep neural networks, because they are feed forward, they cannot do this explaining away dynamically. So what do you have to do? You have to show all combinations of how these characters can come together. So you have to bring the complexity of inference into the training side. You basically, now what you do is you make a very deep neural network and try to show it all combinations of how these captchas can come together, and then maybe it will learn some things about how to explain in a feed forward path. So it's really the dynamism that is missing. Yes, you can basically take that explaining away computation, which is inference, and amortize it by putting it on the training side and make a very deep neural network to mimic that computation. And the trade-off is that you are now bringing it to the cost to the training side. Plus, it is still limited to the distribution that you expose the network to on the training in the training setup. And if there is a distribution shift, it can't do the dynamic inference again. So hopefully that picture fits together.
right. Yeah. Yeah, just my 2 cents on this. I feel another like difference between modern computer vision and human vision or biological vision is that our vision, the foveal vision actually only pays attention to like a small area, right?
Exactly. Yeah.
And when we do convolutions, we actually try to parallelize everything. We try to
Yeah.
just attend to the whole picture
Yeah.
instead of actually, doing saccades or like paying
Correct.
attention to small patches. I
Yeah.
mean, there's some new work on, patch learning and everything, but I
Yeah.
think there's still like a gap between, biological vision and, computer vision.
Oh, absolutely. In fact, convolution is kind of a hack that we have put in biological vision is not convolutional at all because of the phobia. It is not convolutional at all. What the principle that biology uses is local receptive fields. It doesn't mean that the receptive fields are tied in weights or that you are pooling based on the knowledge of what is the correspondence between the filters. No, but so biology is much more general than that one. So yeah, I agree with you, and there are deep insights in why visual system uses a fovea and saccades to build a model of the scene. There are and yes, and that would be a direction in which our models will have to go.
Thank you. Thanks for sharing the secret sauce for breaking CAPTCHA. And we're actually, at least personally, I'm also interested in your work on the hierarchical and temporal models. Could you tell us a little bit more about that?
Yeah, so this was, so the history is that this is where I started my PhD in hierarchical temporal memory was my PhD thesis. And this is work I did at Numenta. I was co-founder of Numenta with Jeff Hawkins, and the company is still running. And so I still believe in many of the core ideas of hierarchical temporal memory. It's only a question of how do you make it into practice? What are the ways in which you can combine insights from machine learning and neuroscience to make it into practice. So Numenta is still developing the HTM hierarchical temporal memory algorithms under that name, whereas they go into more and more biological details on how to implement those algorithms. I look at it at Vicarious, and many of my collaborators look at it from the point of view of more in the context of machine learning, basically saying all the models will be formulated as machine learning models or graphical models, and so that the math of it all works out, but you will import principles from neuroscience to structure the models. So I would say a recursive cortical network is an outgrowth of hierarchical temporal memory at a very high level. But the details of how it comes to how it is formulated and how it is implemented are very, very different because those details matter a lot.
I see. That's interesting. So we touched on this topic a little bit, but how do you envision the future? Like what do you think is the next big idea that AI could borrow from brain sciences, like very specifically?
If it is one big idea, I would say
for a few, yeah, but the emphasis is on borrowing from brain science, right?
Yeah, I would say feedback. Feedback is the one big one, and then when you start pulling on that thread of why feedback is important, many other insights will come with it. So if you just keep pushing on the idea of why is feedback important and why is visual processing or anything in the brain not just a feed-forward path, and if you follow that thread, many other insights will come with it. Like and I would even say compositionality, the idea that you can have primitive representations which are parts based that are combined to form the higher level representations. These are all very intimately connected with feedback, because if it was not compositional, there was no need for feedback. It is because of compositional that not everything is available at the top. You have to come back down to do explaining away. So I would put that as the one thing.
Okay, yeah, I agree. Yeah, I think it's very insightful, and I think more and more people start to realize, the critical rule, or at least start to think about what exactly does feedback do? Why is it so important in in the brain and in artificial neural networks as well, right?
Yeah.
So yeah, I totally agree. And so on that topic, what do you think would be, say, the next milestone in terms of, say, embodiment, or what what a consumer or like a non-expert could expect to see? Is it something like autonomous driving that would arrive first, or more sci-fi robotic pets, or even like, say, humanoid robotic helpers like in some of the movies?
Yeah, so autonomous driving is one example of the thing I think that will take a long time. I don't know whether you will be able to buy a car without a steering wheel in the next 10 years. I highly doubt that because, and this is an example of the long tail, right? This is all these situations, whether it is autonomous driving, unstructured robotics, cleaning up a house, all these have a long tail of challenges which cannot be just brute forced using just more and more data augmentation. And so that means there needs to be fundamental breakthroughs on the way to enable those things. Yes, some domains you can get useful outputs. It doesn't mean none of it, you can still get to acceptable performance levels in some use cases, and that will still drive the development because you can extract value out of them. So I would say it would go from in robotics, it would be earlier it was extremely structured domains. Now it would go to semi-structured domains where errors are okay. It's not like self-driving cars where, oh, an error is catastrophic. Here it will be errors are okay, and you can even have a human in the loop. It's not extreme real time like self-driving cars. So it would go from structured to semi-structured worlds and then kind of gradually expand. It won't be like an instant, oh, here is it suddenly takes, it won't be like the iPhone curve where, when the iPhone came in, within 2 years, things taking over. It will be a gradual taking over, but it will still happen. It will still happen over, I can already see signs of it looking at our sales pipeline. It will, a lot of things are going to get automated using a mix of current deep learning techniques, the advances like the recursive cortical network that we have created, and the advances that will be coming in the next 5 years. A lot of tasks will get automated with that. But self-driving cars might be something that have to wait for longer because of the long tail.
Yeah. I think the long tail, like people also like start to realize, there's generally this long tail distribution in many real world applications and cases, and you just like can't brute force it, as you were saying. Yeah. And what do you expect, or like what do you desire the most, to be realized or embodied in robotics personally?
Yes, I would like to build a robot that can, this is not what we are building, but this is a dream goal. Like walk in a house and clean up the house, which is an extremely hard task. That I would say that is artificial general intelligence. Without damaging the dog or the kids. That's what that is the constraint that you cannot.
I think that's sometimes hard for us to do as well.
Yeah, that's true.
So that could be challenging.
Yeah.
All right. I think we're about time, and let me see if there are some questions in the Q&A and chat. So, okay, so there's a question about some confusion about data regime shift. I'm sorry, there's a gardener outside.
Yeah, so it's basically distribution shift, right? Many of the ML models are trained using one, data we gather from the real world, and then data that we either create by manipulating that data to make data augmentations, and these data augmentations can be either we are just adding transformations to the data we collected, things like contrast change in training image recognition models, or color distribution changes in image recognition models, or we might be creating artificial data to train. And in all this, we are making the assumption that all this data augmentation that we are doing matches the changes that we make in the real world, that occur in the real world. And if they don't, then the collected data might not capture all the variations that actually occur in the real world, and our models won't perform as well in the real world. And that's the problem of distribution shift, and that is related to data efficiency of your model. If your model takes a lot of data to train up, then the model is more susceptible to distribution shifts. So yeah, hopefully that answers the question. I have 2 more minutes before I have to run off.
Okay, let me see if I have one more question. Actually, yeah, I couldn't find one, but I do have a question. So I think previous panelists actually mentioned something, and also some papers show that with just massive amount of data, plus self-supervised learning, you could actually achieve superior performance. And actually, for ImageNet task, the machines or neural networks are already beating human experts, right? Like,
yeah.
Where do you think the effect of just adding more data would stop? Like, what level of performance will we reach just by adding the sheer amount of data and computation, and
Yeah.
at which point, I know you were saying like at some point we have to change how we do things,
Yeah.
right?
Yeah. So this is where the one, these benchmarks are broken in the way that we measure things. Like basically image recognition, object recognition is not better than humans currently. Take any ML model, it is not better than humans. Like there are stories about, oh, it is better than humans. No, if they were better than humans, we would have self-driving cars, because that's the real problem to be solved. That how can you recognize something in context, instead of a stop sign being just recognized as stop sign, basically, oh, that stop sign is stuck to the back of a car. That is a perception problem. So if you measure narrowly, or saying, oh, I need to memorize 500 breeds of dog on ImageNet, then you are measuring the human performance in the wrong way, and human performance might be just degraded because of, oh, they can't distinguish between this is dog breed 1 versus dog breed 2, and so it's a measurement problem. In reality, human performance is way better than current network performance.
Yeah, I think we're more robust, right?
Exactly. And filling that gap between human performance and machine performance, yeah, you can try to do that by data augmenting the heck away, but I don't think that will work. Ultimately, you have to solve some fundamental problems. That's my take.
All right, thank you. We really appreciate that you're joining us today, and we want to be respectful of your time. And thank you again.
Thanks a lot for having me.
Thanks.
Thank you. Thanks, Dilip and Yang, and thank you to everybody who stuck around for the last almost 5 hours with us. And we have these events every quarter. The next one is actually going to be a hybrid one, where we're going to have an in-person event in San Francisco, but also a virtual event. Hope to see you guys there. Again, we're called the State of the Art conference, and it's hosted by Abacus. Thanks everyone for coming, and goodbye.